Good afternoon, everyone. This is Fahim, and this is going to be my submission for the 2023 CarMax Showcase, where we take a look at this dataset with 200,000 entries in it. We're going to clean it up by doing some binning of some of the more redundant variables or some of the variables with a larger number of distinct values that can be summarized easier. After we're done binning those, we are going to be doing principal component analysis to determine if some of these independent variables in the dataset are redundant. We're going to be using both of those aspects we just talked about to perform decision tree modeling. And after all that is done, we're going to be answering the big question: what can the traded car of someone going to CarMax to submit, what can that tell us about the car that they end up purchasing? So starting off this submission, we're going to be taking a look at the dependent and independent variables of this data set. To sum it up, the dependent variables are going to be any of these variables that do not include the word appraisal as part of it, because we're trying to determine what type of car they end up purchasing, and appraisal is the car they're submitting, not purchasing. So that's the difference between the dependent and independent variables. Now what you're going to notice is that some of these variables need to be recoded. To give you an example, price is a range that was given in the data set. The price of the purchase car can go from 0 to 5K, 15 to 20, 20 to 25. There's a lot of these values right here. When you actually go to split some of these variables on the decision tree, if you choose to make them continuous, such as horsepower right here, which has different distinct values, such as 51 horsepower, 52, 53, 54, but the maximum is like 800, so it includes every distinct value as part of the decision tree, that's not going to look pretty. So you have to bin some of these variables in order to really make a decision tree that you can accurately assess. So that is why we categorize most of these continuous variables into categories. So when we upload it to Jump, which is the software we're going to be using, we bin them in Excel, we'll be able to accurately judge the decision tree and perform principal analysis, which is going to be the next thing that we cover right here. Now, principal component analysis is very, 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 very important in all types of machine learning, especially in this project that it took to do right here, but it can be a bit complicated. I'm going to try to explain this in different tiers. For someone easy, I can make it easy for someone to understand. I'll do a bit of a harder method, and then I'll do something for the people who are a bit more savvy in math. So it should encompass a wide audience of people. In its simplest terms, principal component analysis is a method used to compile all the different factors influencing what type of car a person purchases and temporarily removes all the ones that are redundant. It's that simple. So to give you an example, in this data set, there were 14 independent variables, I believe. There might have been one more, if I don't recall it correctly, but some of them might be a bit redundant. If we're thinking about all the different ways we can identify a car, you can do it by, let's say, color and shade. Let's say we call the car black, but also dark at the same time. Well, that's a bit of a redundant statement to use, so instead we'll remove those from the ensemble and perform our analysis without it. That is what PCA is doing. And the great thing about this, the new independent variable that is made using this method is said to be a linear combination of all the others. So there's a bit of linear algebra that goes into that, but what PCA is doing, it's finding all the characteristics, it's compiling them across the 200,000 entries in the most efficient way, and it analyzes all linear combinations, and it will produce values for every single entry that you can use in a decision tree model. And if you were to do a proof of this, where you were to hand draw a scatter plot with all the independent variables and perform regression analysis for the maximum variance of each point and the minimum error, you would get the property associated with PCA. And that's for people who are a bit more math savvy. And what you notice here are these eigenvalues off to the side. And all this is, in the top left right here, these eigenvalues are just a term corresponding to the principal direction which has the most variance. So essentially, around 75% of the data set can be attributed to these two eigenvalues, which is super neat and super, super important. And for the people who are very math savvy in the room, this is related to something we've been seeing since elementary school, when you learn about y is equal to mx plus b. This relates to PCA, where if you sum the values of your b and y terms, and if you're treating m as a constant that you can separate out of your equation, combine the remaining terms, the solution that you're left with will be a summation known as the least square term. And that is basically what your computer is performing. When I did this in Jump, that is what's happening when it produces a row entry for every single term. And the reason why I didn't scroll all the way down in the original Excel sheet that I showed in this video is because the principal component is hiding down here. This is a combination of all the independent variables, which I discussed before, and they're multiplied by a constant term in order to give you a unique entry for every single row in the data set. Now, I'm going to be honest, this is something I don't know. It's a bit out of my scope as an MSAS student, but your computer generates this right here. There's some pretty serious mathematics that goes behind this. I'll have to look into it more, but how the computer generates this using the linear combinations of the independent variables is very, very complicated. That is for the very, very, very math savvy people who want to learn about that. With that being said, once we do decide to make our decision trees in Jump with each of the dependent variables recognized as a target variable, there's one variable, in my opinion, which I think is fluff and should be ignored for decision tree modeling. The model of the vehicle. Now there are so many different models and so many of them overlap with each other, such as, to give you an example of a vehicle model, can someone tell me the difference between a Toyota Corolla SE and Toyota Corolla LE? Yeah, neither can I. That's why some of these overlap with each other. Some of them might have different identifiers, but there are so many different distinct values of these models that if your decision tree splits early with these, I just chose to ignore it. And there were definitely a couple of decision trees that were very good that did not include these as an early splitting criteria. So it definitely is not necessary. And one of the trees I decided to look at is with cylinders as the splitting criteria, leading into horsepower, and what do we have here? The principal component number. The best part about decision tree modeling, and I forgot to mention this earlier, it's fine, I can just do it now, is that this data set has missing values in it. And decision tree modeling, because how it trains the data sets, decision tree modeling does not require missing value imputation because it does not use those as criteria when splitting the rest of the nodes. You will need this for random forest classification and regression analysis because those aren't able to handle the missing value imputation when forming their models. But for decision tree modeling, it's perfectly fine to have them, which is one of the reasons why I went with this, because I didn't want to also have to impute all of the missing variables in the data set. But looking at here, we see that for all vehicles that have a horsepower greater than 235, they lead directly into the principal component number. And those exact vehicles have an even ratio of, or a close to even ratio of 4 to 6 to 8 cylinders in their engines, being around 33%. This is important for the left side of the nodes because it represents that for all vehicles greater than 235 horsepower, there's a lot of different factors that are a linear combination of each other from this principal component number that are going into what people will be purchasing for their vehicle. This is very important because what I think I can summarize this up is if someone goes in to trade a vehicle, they want to buy a more luxurious or powerful vehicle, they're really going to be looking at a bunch of different values when determining it, rather than someone who trades in a vehicle that isn't necessarily worth as much with a low appraisal offer. They're just going to go with a car that does not have as much horsepower, and they're going to stick with the same vehicle that they chose to come in with. So to give you an example, if I go in to trade in an 8-cylinder vehicle, it's most likely going to have a large amount of horsepower, and lo and behold, it's probably going to be a truck or a Ford F-150, or it might be a luxury vehicle such as a V8 Mustang, that's more of a sports car, or a Ferrari, something on those lines, which aligns with the principal component number. So if someone comes up to you and asks you, someone who works at CarMax, hey, how can we customize a customer's experience? First, ask them about the car they want to trade in for general information. After that, You still have to ask them for their price range, which is also a dependent variable. Unfortunately, this is because price range is the easiest to approach a customer from, and out of every decision tree I looked at, because I looked at all dependent variables, the most common splitting criteria in the decision trees was that price factor. After that, I think this is where you should customize the experience to include the engine parameters such as horsepower, cylinders, and then maybe lead into some of the independent variables used in that principal component analysis.